Chapter 4 Axial Load Linear Change, this time in a rectangular cross section. So we want to know if we have a cross section with the information provided, how can we calculate the delta at the end? So again, in delta, we do have a discrete part which comes from axial deformation comes from a summation of different section, and delta which is provided for continuous shape, and that's a integration over the length uh, for uh, p over e a x dx. So in this time we have a non-uniform change in cross-sectional area, for this time a rectangular cross section, and we want to know what is the delta at the free end. So again, if we do know we have a rectangular cross sections at both ends a1 and a sub 2, if we just consider a sample, a cross section for our integration and call that ax, which is with the length of x at the beginning, and the information for the problem is just a p of 62 kilopounds, modulus of elasticity 10,400 ksi, b1 4, b2 6 inches, length 5 feet, and the thickness of plate is a 3/4 of inches. Let's solve the problem parametric at first, and then we'll uh, place the our problem with the numeric values to get the answer. So in that case, we do know for a discrete or a uniform cross section, delta is just PL over EA. Now for our case, d delta, because we need to integrate it, and that's PL over E times A sub x. And how that goes, it delta is just integration of our element of d delta. And if you develop the equation for A sub x from the beginning, that's A1, which is here. Mhm. That's A1 plus the slope of the line A2 minus A1 over the length, which is L1, A2 minus A1 divided by L times x, which is the distance from the beginning. So that gives you the equation for A sub x2, which is A1 plus the A2 minus A1 over L times the distance of travel to the our cross-sectional, our elemental cross-sectional area. So in that case, delta is just if you replace ax at the denominator, you can easily approach the problem. In that case, if again we get a constant out from the integration, and that's delta equal to p over a modulus of elasticity, then times integration from 0 to L. If we call it length of L, that's 0, that's the total L, dx over a sub x. If we call the main equation equation 1, and we call this part of this variable part, the integration part of equation 2, let's see how we can solve 2. That's integration from 0 to L dx over ax. And if you do this integration, it just gives you 2 is equal to ln of a1 plus a2 minus a1 over L times x, mhm, over a2 minus a1 over L from 0 to L. Mhm. That is that that close parenthesis should be here. If I am not wrong. I I think that's the correct one. Yep. So let's keep moving. And if you do the mass, it just gives you 2 is equal to, let's the constant, this is the denominator, it just moves up like a constant, that's L over A2 minus A1, and the integration part just gives you ln of A2 over A1. So if we replace 2 in the main equation right now, we can have delta is equal P over E times L over E2 minus E1, A2 minus A1 times ln of cross-sectional area 2 over cross-sectional area 1. So that's the equation for a non-uniform change in cross-sectional area like what you can observe here. So if we just replace our problem with our numeric value, so that's a force of 62 kilopounds, modulus of elasticity of 10,400 ksi, V1, which is the width of uh, cross-sectional area 1, and B2 is the width of cross-sectional area 2. Length is provided to be 5 feet, and we need to convert it to inches because all the calculation are in inches. And the thickness also is 3/4 of inches. The thickness of the plate is, that's thickness, which is 3 over 4 inches, and that's the width of the plate, which for B2 is 6 inch, for B1 is just a 4 inches. Mhm. And if you replace the numeric value in the delta C equation, because that's C here, and if you replace that in delta C equation, it just gives you delta C is equal to P over A times L over A2 minus A1 times ln of A2 over A1. And ln is Neperian logarithm. So that's 62 over 10, 400 times 5 times 12. That's conversion of 5 feet to 5 to inches, and that's a b minus a1 minus a2. That's 6 minus 4 times 3/4 of inches times ln of a2 over a1 is just 6 over the ratio of b1 because thickness is just cancel out. It's 6 over 2, that's a 3 over 2, that's 1.5. And if you do the math, it gives you point 0.096 inches. So again, for a non-uniform rectangular change in cross-section, you can get the equation, parametric equation, replace it with your own data, and that's a delta C is equal to 0.0967 inches. Thank you.